Hello there. I'm so glad you found your way here, because tonight we're stepping away from the familiar constellations and well-worn paths of astronomy. Instead, we're venturing into the shadows between stars, where the universe keeps its most perplexing secrets, the anomalies, the impossible things, the cosmic riddles that make even scientists pause and whisper, "That shouldn't be there." There's nothing you need to do right now. Just let yourself settle in, let your breathing slow, and allow these strange truths to wash over you like cosmic radiation. Gentle, invisible, but somehow transforming. Tonight, we'll drift through phenomena that break the rules, rogue signals emerging from empty space, quantum events that seem to mock causality, gravitational anomalies that shouldn't exist according to everything we know, and the bizarre behavior of matter at the edge of black holes. Some of these mysteries might capture your imagination. Others might simply become a soft background hum as you relax deeper and deeper. There's no test at the end. No need to remember everything. These are just beautiful, bewildering facts floating through the darkness, and you're welcome to let them carry you wherever you need to go. And if this journey into the strange helps you find rest, consider liking and subscribing. It helps other wanderers find their way to these quiet cosmic mysteries too. Also, I'd love to know where you're tuning in from and what time it is there. It's fascinating to see how these videos connect people from around the world. So let's begin. Let's drift together through the universe's most beautiful impossibilities. The universe has a giant cold spot that defies explanation. In the faint afterglow of the Big Bang, astronomers discovered something that shouldn't be there. A vast patch of sky, spanning hundreds of millions of light years, that's significantly colder than everything around it. This isn't a small variation. It's a massive temperature deficit in the cosmic microwave background, the oldest light we can observe. According to our models of the early universe, such a large cold region should be extremely rare, perhaps even impossible. Some scientists think it might mark the location of an enormous supervoid, a region with far less matter than average. Others wonder if it could be evidence of something more exotic, like the imprint of another universe colliding with ours during the first moments of inflation. Or perhaps it's a crack in our understanding of cosmology itself. The cold spot remains one of the quietest, most persistent puzzles in modern astronomy. Not a glaring error, but a whisper that something about our universe may not be quite what it seems. Some black holes spin so fast they drag space itself. Black holes don't just sit still in the fabric of space-time. Some of them spin, rotating at speeds so tremendous they twist the very structure of space around them. This phenomenon is called frame dragging. And near the most rapidly spinning black holes, it becomes extreme. Space itself gets pulled along like water swirling down a drain, and anything nearby, light, matter, even time, is forced to move with it. These spinning black holes, called Kerr black holes, can rotate at nearly the speed of light at their event horizons. At such speeds, the usual rules begin to blur. There's a region just outside the event horizon, known as the ergosphere, where nothing can remain stationary. Everything is dragged in the direction of the spin, caught in a relentless cosmic current. Particles, photons, even spacecraft, if one ever got close enough, would be swept along, unable to resist. It's not gravity alone that holds them. It's the rotation of space itself. In the quiet dark of the universe, some black holes don't just pull. They spin the cosmos like thread on a wheel. Rogue planets outnumber stars in the galaxy. We usually picture planets orbiting stars, held in place by gravity, warmed by light. But the galaxy is filled with planets that have no star at all. These rogue planets drift alone through interstellar space, ejected from their birth systems by gravitational chaos, or formed in isolation like failed stars. They receive no sunlight. Their skies are eternally dark, lit only by the faint glow of distant galaxies. Some may have thick atmospheres that trap residual heat from their formation, keeping their surfaces warm enough for exotic chemistry. Others are frozen solid, drifting silently through the void. Astronomers estimate there may be billions of these orphaned worlds in the Milky Way, possibly even more rogue planets than stars. They're nearly impossible to detect unless they pass in front of a background star or emit faint infrared radiation. Most remain invisible, wandering the galaxy like ghosts. No sunrise, no seasons. Just an endless night broken only by the occasional flicker of a distant supernova. Each one is a world untethered, spinning alone in the vastness between. Fast radio bursts arrive from across the universe with no clear source. Every so often, radio telescopes pick up something strange. A burst of radio waves, incredibly bright, lasting only milliseconds, arriving from deep space. These are called fast radio bursts, or FRBs, and they're among the most mysterious phenomena in modern astronomy. Each burst releases as much energy in a fraction of a second as the sun emits in days. Some happen once and never repeat. Others flash again and again from the same location, following no obvious pattern. We know they come from distant galaxies, billions of light years away, but we don't know what creates them. Theories range from magnetars, neutron stars with extreme magnetic fields, to colliding black holes, to something far stranger we haven't imagined yet. A few even speculated, half seriously, that they could be artificial, signals from advanced civilizations. Most astronomers think the answer is natural, but we simply don't have enough data. The universe is sending us postcards written in radiolight, brief, brilliant, and cryptic. And so far, we can't quite read the message. Quasars were once mistaken for stars, but outshine entire galaxies when quasars were first discovered in the 1960s. Astronomers thought they were looking at faint, unusual stars within our own galaxy. But when their spectra were analyzed, something astonishing emerged. The light was redshifted far more than expected, meaning these objects weren't nearby at all. They were billions of light years away, and yet still bright enough to be detected. That meant they had to be extraordinarily luminous, outshining entire galaxies despite appearing as mere points of light. What could be so bright? The answer lies at the center of distant galaxies, where supermassive black holes feed on vast amounts of matter. As gas spirals inward, it heats to millions of degrees, glowing brilliantly in visible light, X-rays, and radio waves. This glowing accretion disk is what we call a quasar. Some are so luminous they can be seen from across the observable universe. They're among the most energetic objects known, powered not by fusion like stars, but by gravity's endless appetite. A quasar is a black hole dressed in light, quiet at its core, blazing at its edges. There's a planet where it rains molten glass sideways, far from Earth, in a solar system dozens of light years away. there exists a planet that would feel like a nightmare. HD 189733b is a gas giant, a world slightly larger than Jupiter, locked in a tight orbit around its star. But what makes it truly bizarre is its weather. The planet's atmosphere reaches temperatures over 1000 degrees Celsius, hot enough to vaporize metals. Winds scream across its surface at speeds exceeding 5,000 miles per hour, 7 times the speed of sound. And within those winds, silicate particles condense and fall, not as soft snow, but as molten glass. Sideways, the glass doesn't fall straight down. It's caught in the planet's ferocious jet streams and whipped horizontally through the air, scouring anything in its path. The planet also has a deep blue color, not from water, but from the way its hazy atmosphere scatters light, much like Earth's sky. From a distance, it might look inviting. Up close, it's a hellscape of heat, speed, and glass rain. A reminder that beauty in the universe can be as dangerous as it is strange. Some stars vanish without explanation. Astronomy is built on consistency. Stars follow predictable patterns. They're born, they burn, they die, and we can trace their lives through observation. But every so often, a star simply disappears. Not gradually, not in the supernova, just gone. In recent years, astronomers comparing old images of the sky to new ones have found stars that no longer exist. In one well-documented case, a massive star in a distant galaxy appeared to vanish between observations. No explosion was detected. No remnant was left behind. It was there, and then it wasn't. One possibility is that the star underwent a failed supernova, collapsing directly into a black hole without the usual fireworks. Another is that thick clouds of dust obscured it, though that seems unlikely given the observations. Or perhaps something stranger occurred, something we don't yet have a name for. These vanishing stars challenge our models. They suggest that stellar death may not always be as dramatic or predictable as we thought. In the dark expanse of space, even the lights we think are constant can blink out without warning. A star orbits the Milky Way's black hole in just 12 years. At the center of our galaxy lies Sagittarius A, a supermassive black hole with a mass of over 4 million suns. Around it, stars drift in long, slow orbits, taking thousands or even millions of years to complete a single loop. But one star, known as S2, is different. It orbits incredibly close to the black hole, completing a full orbit in just under 12 years. That might sound slow, but for a star orbiting a black hole, it's breathtaking. At its closest approach, S2 comes within about 17 light hours of the event horizon, traveling at nearly 3% the speed of light. That's fast enough for relativistic effects to become measurable. Time slows down slightly for the star. Its light gets redshifted by the intense gravity. Its orbit doesn't follow a perfect ellipse, but wobbles slightly due to the curvature of space-time. Astronomers have watched S2 for decades, using it as a natural laboratory to test Einstein's theory of general relativity. And so far, the theory holds. In the heart of the galaxy, a single star dances on the edge of oblivion, tracing the shape of space-time itself. There's a vast empty region called the Boötes void. In the constellation Boötes, there's a region of space so empty it's hard to comprehend. Known as the Boötes void, it spans roughly 330 million light-years across and contains only about 60 galaxies. That may sound like a lot, but in a region that size, astronomers would expect to find thousands. It's not that the void is completely empty, dark matter, and a thin scattering of gas still exists there, but it's far more barren than it should be. Why such a massive region contains so few galaxies remains unclear. Some think it formed naturally as matter clumped into denser regions elsewhere, leaving voids behind. Others wonder if it's the result of ancient cosmic events we don't yet understand. From our perspective, the void is a dark patch in the cosmic web, a place where the universe forgot to build. And within that silence, there may be lessons about structure, gravity, and the way matter flows through time. The void is not nothing. It's an absence that speaks. Magnetars are the most magnetic objects in the universe. Neutron stars are already extreme. The collapsed cores of massive stars, incredibly dense and spinning rapidly. But magnetars take it further. These neutron stars have magnetic fields trillions of times stronger than Earth's, the most powerful magnetic fields known to exist. If a magnetar were located halfway to the moon, it could strip the information off every credit card on Earth. If you got too close, the magnetic field would be strong enough to distort your atoms, pulling on the electrons in ways that would fundamentally alter chemistry and biology. These fields are so intense they warp the star's surface, creating starquakes that release bursts of X-rays and gamma rays into space. These flares can be detected across the galaxy. Despite their power, magnetars don't last forever. Their magnetic fields decay over time, and after about 10,000 years they fade into quieter neutron stars. But while they're active, they're among the most violent and energetic objects in the cosmos. Small, dark, and wrapped in invisible force. Not silent, but roaring in wavelengths we can barely perceive. The great attractor is pulling our galaxy towards something unseen. The Milky Way isn't sitting still. Along with thousands of other galaxies, it's moving through space at over 600 kilometers per second, pulled by a mysterious gravitational force known as the Great Attractor. This anomaly lies roughly 150 million light-years away, hidden behind the dense plane of our own galaxy, which blocks much of our view. We can't see it directly, but we can feel its gravitational tug on everything nearby. The Great Attractor itself may not be a single object, but rather a massive concentration of mass, perhaps a cluster of galaxy clusters, that exerts an enormous pull. Beyond it lies an even larger structure, the Shapley supercluster, which may be the true source of the motion. Together, these distant masses create a kind of cosmic river, drawing galaxies toward them over billions of years. We're passengers on that current, drifting slowly, pulled by forces we can measure but not fully see. Somewhere in the dark, something immense waits, and we're moving toward it, gently, inevitably, across the silent expanse of space. Some exoplanets orbit their stars in mere hours. We're used to thinking of planetary orbits in terms of months or years. Earth takes 365 days to circle the Sun. Jupiter takes 12 years. But some exoplanets, known as ultra-short period planets, complete an entire orbit in less than a day. A few take only a few hours. These worlds are scorched, tidally locked, and incredibly close to their host stars, often closer than Mercury is to our Sun. Their surfaces are molten. Their atmospheres, if they have any, are being stripped away by stellar winds. One side always faces the star, baking in perpetual daylight. The other side is cast in eternal shadow. Some of these planets may be the remnants of larger gas giants that migrated inward and had their outer layers blown away, leaving only dense rocky cores. Others may have formed in place, though how that happens is still debated. What's certain is that these planets represent an extreme, worlds where a year passes faster than a single rotation of Earth. Time moves differently there, not because of relativity, but because of proximity, heat, and speed. Neutron stars can spin over 700 times per second. When a massive star collapses, its core can become a neutron star, a sphere of nuclear matter about 20 kilometers wide, but containing more mass than the Sun. And some of these neutron stars spin fast. The fastest known pulsar, PSR J1M482446 AD, rotates 716 times per second. That means its surface is moving at roughly 25% the speed of light. At that speed, the star is nearly at the breaking point. Any faster, and centrifugal forces will begin to tear it apart. How do they spin so fast? When the core collapses, conservation of angular momentum causes it to spin faster, like a figure skater pulling in their arms. If the neutron star is in a binary system, it can also steal matter from a companion star, which adds more spin. These millisecond pulsars are cosmic lighthouses, emitting beams of radiation that sweep across space with each rotation. When those beams point toward Earth, we detect them as regular pulses, ticking with extraordinary precision. In the stillness of the void, some stars beat like drums, faster than any rhythm we could ever follow. Dark flow suggests something beyond the observable universe. The universe is expanding in all directions, and most galaxies appear to be moving in ways consistent with that expansion. But in 2008, astronomers noticed something odd. Clusters of galaxies across a large region of sky seemed to be drifting in the same direction, as if pulled by something far outside the observable universe. This phenomenon was named dark flow. The motion is subtle, only about 600 to 1,000 kilometers per second, but is consistent across vast distances. What could cause it? One possibility is a concentration of mass beyond the edge of what we can see. Something so massive its gravity reaches even into our observable bubble. Another idea is that it's the remnant of inflation, an imprint from the universe's earliest moments that affects large-scale structure. Some researchers question whether dark flow is real at all, suggesting it could be a measurement artifact. But if it is real, it means there's something out there, beyond the cosmic horizon, influencing our motion, something we can feel but never see. Hypervelocity stars are ejected from the galaxy at millions of miles per hour. Most stars orbit the galaxy in steady, predictable paths, but a few have been flung outward at incredible speeds, fast enough to escape the Milky Way entirely. These are called hypervelocity stars, and they're moving at over 1 million miles per hour. How does a star get moving that fast? One way is through a close encounter with the supermassive black hole at the galaxy's center. If a binary star system strays too close, the black hole's gravity can capture one star and fling the other away like a slingshot. Another possibility is a supernova in a binary system, where the explosion kicks the surviving star into space. Once ejected, these stars travel alone, leaving the galaxy behind. Some may wander the intergalactic void for billions of years, carrying with them the memory of a violent encounter. They're exiles, cast out by gravity, drifting through the dark with no way home. But they're not lost. They're just moving too fast to ever stop. Some galaxies contain almost no dark matter. Dark matter is thought to be the invisible scaffold that holds galaxies together. Without it, galaxies wouldn't have enough gravity to keep their stars from flying apart. But in recent years, astronomers have discovered galaxies that seem to defy this rule. Galaxies that appeared to contain little to no dark matter at all. One such galaxy, NGC 1050 DF2, has stars that move at speeds consistent with only the visible matter present. There's no sign of the extra gravitational pull that dark matter should provide. This discovery was unexpected and controversial. Some scientists think the dark matter was stripped away during a past collision. Others suggest these galaxies formed in unusual environments where dark matter never accumulated. A few wonder if our understanding of dark matter is incomplete. These anomalies don't disprove dark matter's existence, but they complicate the picture. They remind us that the universe still holds surprises, and that even our most fundamental assumptions may need refining. In the quiet corners of the cosmos, exceptions exist, and they challenge what we think we know. There's a planet made almost entirely of diamond. In the distant star system, orbiting a pulsar, there's a planet unlike any other. Astronomers believe it's composed largely of crystalline carbon, essentially a giant diamond. This isn't speculation. The planet's mass and density, combined with its likely formation history, suggest it's the remnant core of a star that was once part of a binary system. Over time, the pulsar stripped away the outer layers of its companion, leaving only the dense core behind. Under immense pressure, carbon within that core crystallized. The result is a world that deep inside may consist of vast diamond structures stretching for thousands of kilometers. It doesn't sparkle. It's far too hot and dark for that. But chemically, structurally, it's diamond. This planet reminds us that the universe's diversity extends even to geology. A world made of rock, a world made of gas, and sometimes a world made of crystal, forged in fire and left to orbit in silence, a jewel in the dark that no one will ever hold. The WOW signal remains unexplained after nearly 50 years. On August 15, 1977, a radio telescope in Ohio detected something extraordinary. A strong, narrowband signal from the direction of the constellation Sagittarius, lasting 72 seconds. It was so striking that astronomer Jerry Amon circled it on the printout and wrote "Wow" in the margin. The signal has never been detected again. It matched the kind of transmission scientists expected from an extraterrestrial civilization. Focused, powerful, and at a frequency where natural sources are rare. But despite decades of follow-up observations, the WOW signal has never repeated. Some think it was a passing comet releasing hydrogen, though that theory has been challenged. Others suggest it was interference, or a one-time astrophysical event we don't understand. A few still hold out hope that it was, in fact, a message. What makes the WOW signal so tantalizing is its uniqueness. It appeared once, spoke clearly, and vanished. Whether it was a whisper from another world or a cosmic coincidence, we may never know. But it remains one of the most intriguing anomalies in the search for extraterrestrial intelligence. A question mark written in radio waves. Some black holes may contain wormholes instead of singularities. At the heart of every black hole, according to general relativity, lies a singularity, a point of infinite density where the laws of physics break down. But some physicists wonder if that's the full story. What if, instead of a singularity, the center of a black hole contains something else? A wormhole, perhaps, a tunnel connecting to another region of space-time. This idea isn't proven, and it may not even be possible. But mathematically, certain solutions to Einstein's equations allow for it. if a black hole rotated fast enough, or if quantum effects played a role we don't yet understand, the singularity might be replaced by a passage, a bridge to elsewhere. Crossing it would still be fatal. The tidal forces and radiation would destroy anything that tried, but the structure itself might be different than we imagine. This idea touches on one of the deepest mysteries in physics. What really happens at the center of a black hole? We can't observe it. We can only calculate, speculate, and wonder. And in that wondering, the possibility remains that even the darkest objects in the universe might hide doorways. A mysterious hum fills the universe space isn't silent. It's filled with radiation, particles, and fields. But there's also something stranger, a faint, persistent signal that permeates the cosmos. Astronomers call it the cosmic radio background, a diffuse glow of radio waves coming from all directions. Some of it comes from known sources, galaxies, quasars, supernova remnants, but a portion of it remains unexplained. Where does this excess radio emission come from? It could be the combined light of countless faint, distant galaxies too dim to detect individually. Or it might be something more exotic, emissions from the early universe, or from processes we haven't yet identified. The signal is faint, but it's there, a kind of static hum underlying everything else. It's not a message, not a signal in the purposeful sense. But it's a reminder that the universe is never truly quiet. Even in the emptiest regions of space, there's a background murmur, a frequency humming just below perception, like the sound of the cosmos breathing. Some stars blink out and reappear years later. In the 20th century, astronomers began cataloguing stars with unusual behavior, and among them were objects that seemed to vanish and then return. Not in the gradual way of a variable star, but suddenly, as if switched off. One example is the star KC 8462852, also known as Tabby star, which exhibited massive, irregular dimming events. Its brightness dropped by up to 22%, far more than could be explained by a planet passing in front of it. The dimming events were unpredictable and asymmetric, and the star's light would return days or weeks later. While dust clouds are now the leading explanation, the mystery sparked intense interest. Other stars have shown similar behavior, appearing to blink out for years before reappearing. Some may be obscured by dense clouds of gas or debris. Others could be part of binary systems where the companion periodically blocks the light. But in a few cases, no explanation fits neatly. These blinking stars challenge our ability to predict cosmic behavior. They remind us that even something as stable as starlight can flicker in ways we don't fully understand. Oumuamua accelerated for no obvious reason. In 2017, astronomers detected the first known interstellar object to pass through our solar system. It was small, elongated, and moving fast, tumbling through space on a trajectory that clearly originated from beyond the sun's influence. They named it Oumuamua, Hawaiian for scout, but as scientists tracked its path, something strange happened. Oumuamua accelerated. Not much, but enough to be measured. This slight boost in speed couldn't be explained by gravity alone. When comets accelerate, it's because they're venting gas as they heat up near the sun, creating a small rocket effect. But Oumuamua showed no signs of outgassing, no tail, no coma. So what pushed it? Some suggested it could be a very unusual comet with a different kind of ice. Others proposed it was a fragment of a shattered planet, or even a light sail. a thin reflective structure propelled by starlight. That last idea, while speculative, captured the imagination of many. Was Oumuamua natural, or could it have been artificial? We may never know. It's long gone now, speeding back into interstellar space. But it left behind a trail of questions and a reminder that the universe still surprises us. Gamma-ray bursts are the most powerful explosions since the Big Bang. For a few seconds, sometimes less, a gamma-ray burst outshines everything else in the universe. These are the most energetic events we know of, releasing more energy in moments than the sun will emit in its entire lifetime. They occur when massive stars collapse into black holes, or when two neutron stars collide, creating jets of radiation that blast outward at nearly the speed of light. If one of these jets is pointed toward Earth, we see a brilliant flash of gamma rays, followed by an afterglow in X-rays, visible light, and radio waves. The burst itself is brief, but the consequences ripple outward for light years. Gas is heated, atoms are ionized, and shock waves spread through the surrounding space. If a gamma ray burst occurred too close to Earth, it could strip away the ozone layer and trigger a mass extinction. Fortunately, they're rare and distant, but they serve as a stark reminder that the universe is capable of sudden, overwhelming violence. In the dark, quiet void, these explosions blaze like cosmic fireworks, brief, brilliant, and almost incomprehensibly powerful. Some exoplanets orbit dead stars. When a star dies, you'd expect its planets to be destroyed or flung into space, and often they are. But astronomers have discovered planets orbiting white dwarfs, the faint remnants of stars like our Sun. These planets somehow survived their star's death. During the red giant phase, the star would have swelled enormously, potentially engulfing inner planets. Yet these worlds endured, either because they were far enough away, or because they migrated inward afterward. Some may be the cores of gas giants, stripped of their atmospheres. Others might have formed from the debris left behind after the star's outer layers were shed. These planets orbit in silence, circling a dim ember that no longer burns. The white dwarf provides little warmth, just the fading heat of a star that once blazed. It's a haunting image. Worlds that witnessed their suns collapse and lived to tell the tale, still bound by gravity, still circling in the afterglow of stellar death. There are stars older than the universe should allow. According to our best measurements, the universe is about 13.8 billion years old, but a few stars appear to be older than that. These ancient stars, known as metal-poor stars, contain almost no elements heavier than hydrogen and helium, suggesting they formed very early in cosmic history. By studying their composition and brightness, astronomers can estimate their ages. And in some cases, those estimates come uncomfortably close to, or even exceed, the age of the universe itself. This creates a paradox. A star can't be older than the universe it exists in. So something is wrong. Either our age estimate for the universe, our age estimate for the stars, or our understanding of stellar evolution. Most likely, the error lies in how we measure stellar ages, which involves complex models and uncertain variables. But the tension remains unresolved. These ancient stars sit at the edge of cosmic time, relics from the universe's earliest chapters. And in their quiet glow, they pose a question we're still trying to answer. Time dilation near black holes can span millennia. Near the event horizon of a black hole, time behaves in ways that defy everyday intuition. According to Einstein's theory of general relativity, the stronger the gravitational field, the slower time flows relative to a distant observer. Near a supermassive black hole, this effect becomes extreme. If you could hover just outside the event horizon for what felt like an hour to you, centuries or even millennia might pass in the universe beyond. This isn't science fiction. It's a measured, predicted consequence of gravity's effect on space-time. Astronauts orbiting Earth experience this on a tiny scale, aging microseconds less than people on the ground. But near a black hole, the difference becomes profound. Time stretches, bends, nearly stops. To an outside observer, you would appear frozen, your movement slowing to an imperceptible crawl. But from your perspective, time would feel normal. It's only when you returned, if you could, that the true cost would be revealed. Everyone you knew would be gone. The world would have aged without you. In the shadow of a black hole, time becomes a prison, measured not in moments, but in the passage of worlds. The Fermi paradox asks why we haven't found anyone. The universe is vast, ancient, and filled with billions of galaxies, each containing billions of stars. Many of those stars have planets, and many of those planets likely have conditions suitable for life. Given the sheer numbers, it seems almost certain that intelligent civilizations should exist somewhere out there. And yet, we've detected no signals, no probes, no evidence. This puzzle is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The silence is strange, even unsettling. Maybe life is far rarer than we think. Maybe intelligence is a brief flicker that rarely survives long. Maybe advanced civilizations avoid contact or exist in ways we can't detect. Or perhaps we're simply looking in the wrong places, listening at the wrong frequencies, asking the wrong questions. The paradox doesn't have an answer yet, but it frames one of humanity's deepest curiosities. Are we alone, or are we just not listening carefully enough? In the quiet of space, the absence of voices is as mysterious as any signal could be. Hawking radiation means black holes slowly evaporate. Black holes seem eternal, inescapable, consuming everything that crosses their event horizon. But according to physicist Stephen Hawking, they don't last forever. Quantum effects near the event horizon allow black holes to emit faint radiation, now called Hawking radiation. This happens because of particle-antiparticle pairs that briefly appear in empty space due to quantum fluctuations. Normally, these pairs annihilate each other almost instantly. But near a black hole, one particle can fall in while the other escapes. To an outside observer, it looks like the black hole is emitting radiation. Over unimaginably long timescales, this process causes the black hole to lose mass. The smaller it gets, the faster it radiates, until eventually it evaporates completely in a final burst of energy. For a black hole the mass of the Sun, this would take about 10 to the power of 67 years, far longer than the current age of the universe. But the principle remains. Even the darkest, most permanent seeming objects are, in a sense, temporary. They glow faintly, losing themselves particle by particle, until nothing remains but the memory of gravity. Some planets orbit two suns like Tatooine. In science fiction, twin sunsets are the stuff of imagination. But in reality, they exist. Astronomers have discovered planets orbiting binary star systems, worlds that circle two suns instead of one. These are called circumbinary planets, and they're more common than we once thought. One well-known example is Kepler-16b, a cold gas giant about 200 light-years away. From its surface, if you could stand there, you'd see two suns moving across the sky, casting double shadows and creating a complex dance of light and dark. The orbital mechanics are intricate. The planet must navigate the gravitational pull of both stars, which orbit each other while the planet orbits them both. This makes the system dynamically unstable over long timescales, but some configurations can remain stable for millions or billions of years. These worlds challenge the traditional picture of planetary formation. They show that planets can emerge even in chaotic environments, and they remind us that the universe's imagination often surpasses our own. Twin suns rising over alien horizons, not fantasy, but fact. The universe may be a hologram. It sounds like something from a movie. But some physicists seriously consider the possibility that our three-dimensional universe is actually a projection from a two-dimensional surface. This idea, known as the holographic principle, emerged from studies of black holes. When matter falls into a black hole, information about it seems to be encoded on the event horizon, the black hole's surface, rather than in its volume. This suggests that the information content of a region of space is proportional to its surface area, not its volume. If that's true for black holes, could it be true for the entire universe? Some theories suggest that all the information in our 3D cosmos could be encoded on a distant 2D boundary. What we perceive as depth, space, and even time might emerge from something fundamentally simpler and flatter. It's a radical idea and far from proven, but it's taken seriously in theoretical physics, especially in the study of quantum gravity. If the universe is a hologram, then reality as we experience it is not fundamental, but derived, a projection of something deeper and stranger we can't yet fully see. Quark stars might exist between neutron stars and black holes. When a massive star collapses, it can form a neutron star, where matter is squeezed so tightly that protons and electrons merge into neutrons. But some physicists wonder if there's another step. If the pressure becomes even more extreme, the neutrons themselves might break apart into their constituent quarks, creating a quark star. These hypothetical objects would be even denser than neutron stars, with cores made of a strange soup of free quarks instead of bound particles. Some might contain strange quarks, forming what's called strange matter, a substance that's more stable than normal matter under extreme conditions. If quark stars exist, they'd be incredibly difficult to distinguish from neutron stars. They'd be small, dense, and emit similar kinds of radiation, but their internal structure would be fundamentally different. We haven't confirmed the existence of a quark star yet, but a few candidates have been identified based on their unusual properties. They'd represent a missing link in the hierarchy of collapsed matter, a state between the familiar and the unknowable. A star that's not quite a neutron star, and not yet a black hole, but something in between, quiet, dense, and strange. The axis of evil suggests the universe isn't random. When scientists mapped the cosmic microwave background in detail, they expected to find a nearly uniform glow with small, random fluctuations. And they did, mostly. But they also found something unexpected. A pattern of temperature variations that seemed to align along a specific axis in space. This alignment, nicknamed the axis of evil by frustrated cosmologists, shouldn't exist. According to the standard model of cosmology, the early universe was uniform in all directions. Any patterns should be random, with no preferred orientation. But this axis suggests a kind of cosmic structure or alignment that we can't explain. Some think it's a statistical fluke, an artifact of how we measure and interpret the data. Others wonder if it points to something deeper, perhaps a feature imprinted during inflation, or evidence that the universe has a structure on scales larger than we can observe. It's a subtle anomaly, but it nags at the edges of cosmology, a whisper that the universe, for all its randomness, may contain hidden order we've only begun to glimpse. Pulsars are the universe's most accurate clocks. When neutron stars spin, they emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like lighthouse beams. If Earth happens to lie in the path, we detect regular pulses of radio waves, X-rays, or gamma rays. These objects are called pulsars, and they are astonishingly precise. Some pulsars, especially millisecond pulsars, keep time more accurately than the best atomic clocks on Earth. Their pulses arrive with such regularity that astronomers can predict them to within microseconds, even years in advance. This precision makes pulsars useful for all kinds of research, from testing relativity to searching for gravitational waves. Any wobble or delay in a pulsar's timing can reveal the presence of orbiting planets, companion stars, or ripples in space-time itself. Pulsars are nature's metronomes, ticking away in the dark with mechanical consistency. They're the remnants of dead stars, but they still serve a purpose, marking time across the cosmos, steady and silent, like the heartbeat of the universe itself. White holes may be the time-reversed twins of black holes. Black holes pull everything in. Nothing escapes once you cross the event horizon. But mathematically, Einstein's equations allow for the opposite, a white hole. This hypothetical object would be a region of space-time from which matter and light can only exit, never enter. It's the time-reversed mirror of a black hole. Where a black hole is a one-way entrance, a white hole would be a one-way exit. No evidence for white holes has ever been found, and most physicists doubt they exist in nature. If they did, they'd be incredibly unstable. Any matter or radiation trying to approach would be repelled by the outward flow, creating a kind of barrier. Some speculate that white holes might have existed briefly in the early universe, or that they could form at the other end of a black hole in a separate region of space-time. Others think they're purely mathematical curiosities with no physical counterpart. Still, the idea lingers. Somewhere in the abstract landscape of general relativity, white holes wait, elegant, impossible, and endlessly intriguing. Red sprites and blue jets are strange atmospheric phenomena. High above thunderstorms, far above the clouds most of us see, strange lights flicker in the upper atmosphere. They're called red sprites and blue jets, and they're a kind of electrical discharge that occurs between the tops of storm clouds and the edge of space. Red sprites appear as brief, red flashes, sometimes branching like jellyfish tendrils, lasting only milliseconds. Blue jets shoot upward from cloud tops in narrow cones of blue light. These phenomena were long dismissed as optical illusions or pilot error, but in the 1990s, high-speed cameras finally captured them. They're real, and they're strange. The mechanisms aren't fully understood, but they seem to be related to lightning activity below, creating brief bursts of ionization in the thin upper atmosphere. They're too high and too brief to pose any danger, but they add a layer of mystery to the sky. Above every storm, in the thin air near space, the atmosphere glows and flickers, a light show unseen by most, playing out in silence. Some supernovae leave no remnant at all. When a massive star explodes, it usually leaves something behind. A neutron star, a black hole, or a glowing nebula of ejected material. But some supernovae seem to leave nothing. These are called pair instability supernovae, and they occur in the most massive stars, those with more than about 130 times the Sun's mass. In these stars, the core becomes so hot that gamma rays spontaneously create particle-antiparticle pairs. This process removes energy and pressure, causing the core to collapse. But instead of forming a black hole, the collapse triggers a runaway thermonuclear explosion, so powerful it tears the entire star apart. Nothing remains. No core, no remnant, just expanding debris scattered into space. These explosions are rare, and we've only detected a few candidates, but they represent the most complete form of stellar destruction possible. A star doesn't just die. It ceases to exist, transformed entirely into light, heat, and scattered atoms, leaving no trace but the glow of its final moment. Cosmic strings might exist as defects in space-time. In the moments after the Big Bang, as the universe cooled and expanded, it may have developed defects, one-dimensional cracks in the fabric of space-time called cosmic strings. These hypothetical objects would be incredibly thin, far thinner than an atom, but immensely dense and long, stretching across vast distances. A cosmic string passing through the solar system could gravitationally perturb the orbits of planets. If one passed near Earth, it could create visual distortions, bending light from distant stars into double images. Cosmic strings, if they exist, would be remnants of symmetry breaking in the early universe, frozen in flaws from when physical forces separated into the forms we know today. No cosmic strings have been definitively detected, but astronomers search for their signatures, gravitational wave signals, or unusual lensing patterns. If found, they'd offer a direct glimpse into the universe's infancy, a scar from the first moments, still lingering in the fabric of space. Some galaxies collide in slow motion over millions of years. Galaxies seem static, frozen in images captured by telescopes, but they're moving, and sometimes they collide. These collisions happen on timescales of millions or even billions of years, too slow to watch in real time, but visible when we compare images taken decades or centuries apart. When two galaxies merge, their stars rarely collide directly. Space is so vast that stars pass by each other like raindrops in a storm. But the gravitational interaction distorts both galaxies, stretching them into long tidal tails, triggering bursts of star formation, and sometimes feeding the supermassive black holes at their centers. Eventually, the two galaxies blend into one, their stars, gas, and dark matter mixing together to form a new, larger galaxy. Our own Milky Way is on a collision course with the Andromeda Galaxy. In about 4 billion years, they'll begin to merge. The night sky will change. New stars will form. But life on Earth, if it still exists, might not even notice the individual stars passing by at such vast distances. A collision that reshapes galaxies, unfolding softly, almost gently, across the ages. Tabby's star still hasn't been fully explained, In 2015, citizen scientists analyzing data from the Kepler Space Telescope noticed something strange. A star named KIC 8462852, later called Tabby's star after astronomer Tabitha Boyajian, was dimming in bizarre irregular patterns. It would lose up to 22% of its brightness, sometimes for days, sometimes for weeks, and the dips were asymmetric, unlike anything caused by a planet. Theories flooded in: a swarm of comets, a shattered planet, dust clouds. Some even suggested, half seriously, that it could be an alien megastructure, something like a Dyson swarm partially blocking the star's light. Follow-up observations favored a natural explanation, likely clouds of dust in orbit around the star, but the exact cause remains unclear. What makes Tabby's star so compelling is how it resists easy answers. Every model fits some of the data, but none fits all of it. The star continues to dim and brighten unpredictably, keeping astronomers guessing. It's a reminder that even with our best instruments, some stars simply refuse to behave the way we expect. The universe's expansion is accelerating for unknown reasons for decades. Astronomers assumed the universe's expansion was slowing down. Gravity, after all, should pull everything back together, or at least slow the expansion over time. But in the late 1990s, observations of distant supernovae revealed something shocking. The expansion wasn't slowing, it was speeding up. This discovery won the Nobel Prize and introduced one of the deepest mysteries in modern cosmology. What's causing the acceleration? The leading explanation is dark energy, a mysterious force that permeates all of space and pushes everything apart. But no one knows what dark energy actually is. It could be a property of space itself, a cosmological constant, or it could be a dynamic field that changes over time. Some theories even suggest our understanding of gravity might be incomplete. Whatever the cause, the effect is clear. The universe is not just expanding, it's accelerating. Galaxies are drifting apart faster and faster, and over trillions of years, the cosmos will grow cold, dark, and unimaginably vast. The universe is running away from itself, and we don't know why. Strange matter could convert everything it touches in the hearts of neutron stars under unimaginable pressure. A bizarre form of matter might exist, strange matter composed of up, down, and strange quarks in roughly equal numbers. Ordinary matter contains only up and down quarks, but strange matter, if it exists, could be more stable. And if it's more stable, that opens a terrifying possibility. A single piece of strange matter, called a strangelet, might convert ordinary matter into more strange matter on contact. One touch, and a chain reaction begins, spreading atom by atom until everything nearby has been transformed. This idea, though speculative, has been seriously considered. Some worry that high-energy particle collisions, like those at the Large Hadron Collider, could create strangelets. But decades of research and countless collisions have produced no evidence. Most physicists believe strange matter, if it exists at all, is confined to the cores of neutron stars, unable to escape or interact with normal matter. Still, the idea lingers, a reminder that under the right conditions, matter itself might not be as stable as it seems. Rogue black holes might drift unseen through the galaxy. Most black holes form when massive stars collapse, and many remain in the regions where they were born. But not all. Some black holes can be ejected from their birthplaces, flung into space by the gravitational chaos of star clusters, or the recoil of a merger. These rogue black holes wander the galaxy alone, invisible, and nearly undetectable. Without matter to consume, they emit no light. Without a companion star, they produce no X-rays. They're ghosts, moving silently through interstellar space. Occasionally, one might pass through a gas cloud, pulling in material and flaring briefly before vanishing again into the dark. Astronomers estimate there could be hundreds of millions of black holes in the Milky Way, many of them rogue. Most will never be found. They pose no threat. Space is so vast that the odds of Earth encountering one are astronomically small. But the thought is quietly unsettling. Somewhere out there, invisible gravitational wells drift through the night, unbound, unseen, and utterly silent. The WOW signal might have been a natural fluke or a one-time transmission. That August night in 1977, the Big Ear radio telescope captured a signal so compelling, it earned an exclamation written by hand. But in nearly 50 years, despite numerous searches, that exact signal has never been detected again. If it was natural, like a burst from a rotating neutron star, or an unusual flare, it would likely have repeated or shown some pattern. If it was a transmission from an intelligent source, we'd expect follow-up attempts, or at least a longer message. Instead, we got 72 seconds of narrowband radio energy, and then silence. Some researchers think the signal might have been a one-time broadcast, perhaps a test transmission, or a beacon aimed elsewhere that we happen to intercept. Others lean toward natural explanations we haven't yet identified. The truth is, we simply don't know, and that ambiguity is what makes it so tantalizing. A single moment of clarity in the noise, followed by decades of silence. Whether it was a message or a fluke, it remains a symbol of our search for contact and of how little we truly know about what's out there. Primordial black holes might explain dark matter. Dark matter is one of the universe's greatest mysteries. It doesn't emit light, doesn't absorb it, and doesn't interact with normal matter except through gravity. But what if it's not a particle at all? What if it's made of black holes? Specifically, primordial black holes, formed in the first moments after the Big Bang. Unlike black holes that form from collapsing stars, primordial black holes could be much smaller, some as tiny as subatomic particles, or much larger. If enough of them formed in the early universe and survived to the present day, they could account for the missing mass we attribute to dark matter. This idea has been tested extensively. Searches for gravitational lensing effects, where a black hole passes in front of a distant star and magnifies its light, have ruled out certain mass ranges, but other ranges remain open. It's possible that a portion of dark matter consists of these invisible, ancient black holes drifting through the cosmos since time began. Not new, but primordial fossils from the dawn of existence. Vacuum decay could end the universe in an instant. Our universe exists in a particular state, what physicists call a quantum vacuum. But there's a possibility, purely theoretical, that this vacuum isn't the lowest energy state. It might be a false vacuum, stable for now, but not truly stable. If that's true, then at any moment, anywhere in the universe, a tiny region could spontaneously transition to a lower energy state, the true vacuum. When that happens, it would create a bubble of new physics, expanding at the speed of light. Inside the bubble, the laws of nature would be different. Atoms might not hold together. Forces could change. Everything would be destroyed and restructured according to new rules. The bubble would grow, consuming galaxies, stars, and everything in its path. there'd be no warning. By the time we saw it coming, it would already be here. This scenario is called vacuum decay, and while it's speculative, it's not ruled out by physics. Fortunately, the universe has existed for nearly 14 billion years without this happening, which suggests our vacuum is either truly stable or at least very long-lived. But the possibility remains, a silent, invisible threat waiting in the quantum foam. Some planets rain iron on distant worlds, where temperatures soar into the thousands of degrees. Rain doesn't fall as water, it falls as molten iron. These exoplanets, called hot Jupiters, orbit extremely close to their stars. On the day side, metals vaporize into the atmosphere, but on the cooler night side, they condense and fall as metallic rain, liquid droplets of iron, magnesium, and other elements. The planet WASP 76b is one such world. It's tidally locked, with one face always toward its star. Powerful winds carry vaporized iron from the day side to the night side, where it cools and precipitates. The result is a sky filled with glowing metal clouds and falling iron rain, a landscape more alien than almost anything we've imagined. These planets challenge our understanding of atmospheric chemistry and weather. They remind us that what we consider normal, rain, clouds, seasons, is specific to Earth. Elsewhere, the universe has invented stranger versions, skies that bleed metal, storms of glass, and twilight zones where elements shift from gas to liquid in the span of miles. The Big Rip could tear the universe apart if dark energy continues to accelerate the universe's expansion, and if that acceleration itself increases over time, the cosmos could face a violent end. This scenario is called the Big Rip. As expansion accelerates, the distances between galaxies grow faster and faster. Eventually, galaxies themselves would be torn apart, then solar systems, then planets, then molecules, atoms, and finally, even subatomic particles. Everything would be pulled apart by the runaway expansion of space itself. The Big Rip isn't certain. It depends on the nature of dark energy, which we don't fully understand. If dark energy is constant, the universe will expand forever, but gently. If it strengthens over time, the Big Rip becomes possible. Current observations suggest we're safe, for now. But in tens of billions of years, if the acceleration continues to grow, the universe could unravel completely. Not in fire or ice, but in a tearing, a dissolution of structure itself. Everything pulled apart, atom by atom, until nothing remains but space, stretching endlessly into the void. Gravitational waves let us hear the universe. For most of history, astronomy was about seeing. We observed light from stars, planets, and galaxies, building our understanding from photons. But in 2015, we gained a new sense. The LIGO detectors made the first direct observation of gravitational waves, ripples in space-time caused by the collision of two black holes over 1 billion light-years away. These waves aren't light. They're distortions in the fabric of space itself, stretching and squeezing everything they pass through by the tiniest amounts. LIGO detects these changes using lasers and mirrors, measuring shifts smaller than the width of a proton. When gravitational waves pass through, the signal creates a kind of sound, a chirp that rises in pitch and amplitude before cutting off. Scientists call this listening to the universe. Each wave carries information about the event that created it, the masses of the black holes, how fast they were spinning, even how far away they were. Gravitational wave astronomy is still young, but it's already transformed our understanding of the cosmos. we're no longer just watching the universe. We're hearing it, feeling its vibrations, sensing the collisions and mergers that ripple across space-time like echoes in a vast, invisible ocean. There are planets orbiting in the habitable zones of dead stars. The habitable zone is the region around a star where liquid water could exist on a planet's surface. We usually think of this zone around living stars like the Sun, but even dead stars, white dwarfs, have habitable zones. They're much closer in because white dwarfs are faint and cool, but they're stable and they last for billions of years. Astronomers have found evidence of rocky material and possibly even planets orbiting white dwarfs. Some of these objects may lie within the habitable zone. If a planet survived its star's red giant phase, or if new planets formed from the debris afterward, life might be possible. It would be a strange existence, orbiting the remnant of a dead sun, but not impossible. The planet would need a thick atmosphere to retain heat. The star would appear small and dim, perhaps reddish or bluish depending on its temperature. But the light would be steady and time would be abundant. In the quiet aftermath of stellar death, life might find a way to begin again, or to persist in the glow of a fading ember. Some black holes spin backward relative to their galaxy. Most black holes rotate in the same direction as the material around them. It makes sense. They formed from collapsing matter that was already spinning. But a few black holes have been found spinning in the opposite direction from their accretion disks or host galaxies. This backward spin is strange, and it suggests a violent history. One possibility is that the black hole experienced a major collision or merger that reversed its rotation. Another is that it consumed material from a different direction, perhaps from a companion star with a retrograde orbit. Backward spinning black holes behave differently. The interaction between the black hole spin and the accretion disk can suppress jet formation or alter how energy is released. They're rare, but they exist, spinning against the current like cosmic rebels. In a universe governed by rotation and angular momentum, these backward spinners remind us that chaos and collision can reshape even the most fundamental motions. Direction, it seems, is not always inherited. Sometimes it's reversed. The cosmic microwave background contains hidden patterns. When we look at the cosmic microwave background, we see a nearly uniform glow with tiny temperature fluctuations. These fluctuations are the seeds of all structure, the slight differences in density that eventually became galaxies. But hidden within that glow are patterns we're still learning to read. There are acoustic peaks, evidence of sound waves traveling through the early universe. There are polarization patterns, swirls and curls in the light that reveal how photons scattered off electrons. And there may be signals from even earlier events, imprints from inflation, or from quantum fluctuations magnified to cosmic scales. Some researchers look for circular patterns that might indicate collisions with other universes before the Big Bang. Others search for statistical anomalies, deviations from randomness that could hint at deeper physics. The CMB is a fossil, the oldest light we can observe. And like any fossil, it holds clues about what came before. We've decoded much of it, but the faintest signals, the subtlest patterns still elude us. Somewhere in that ancient glow, more secrets wait. Hypergiants are so large they're barely held together. The largest stars in the universe are called hypergiants, and they're almost too big to exist. Stars like UY Scuti or Stephenson 2 to 18 are so enormous that if placed where our Sun is, they would extend past the orbit of Jupiter, possibly even Saturn. But their size makes them unstable. These stars have very low density. Their outer layers are so loosely bound that strong stellar winds constantly blow material into space. They lose mass rapidly, shedding the equivalent of Earth's mass every few thousand years. Their atmospheres pulse and fluctuate. Their surfaces are turbulent, covered in enormous convection cells the size of our entire solar system. Hypergiants don't last long, astronomically speaking. They burn through their fuel in just a few million years before collapsing or exploding as supernovae. They exist at the edge of what's physically possible for a star, held together only by their immense gravity, but constantly tearing themselves apart from within. They're beautiful, brief, and on the verge of destruction. Giants live in on borrowed time. The universe might be curved in the ways we can't detect. We experience space as flat, or at least mostly flat. Parallel lines stay parallel. Triangles add up to 180 degrees. But on cosmic scales, space might be curved. If the universe contains enough matter and energy, it could curve back on itself like the surface of a sphere, a closed universe. If it contains less, it might curve outward like a saddle, an open universe. Current measurements suggest the universe is almost perfectly flat, but there's a margin of error. It's possible the curvature is so slight we can't measure it yet. If the universe is closed, traveling far enough in one direction would eventually bring you back to where you started, not by crossing an edge, but by following the curvature of space. If it's open, space extends infinitely in all directions. We don't know which is true. But the question shapes how we think about the cosmos. Is it finite or infinite? Bounded or endless? The answer lies in measurements so precise they push the limits of our technology, and in the subtle geometry of space itself. Some neutron stars have mountains just millimeters tall. Neutron stars are incredibly smooth. Gravity is so strong that it pulls everything toward the center, flattening any irregularities. But they're not perfectly smooth. Some have tiny imperfections, mountains that rise above the surface. These mountains aren't like Earth's. They're only millimeters tall, a fraction of an inch. But given the neutron star's extreme gravity, even a millimeter-tall mountain represents an enormous amount of mass and strain. These tiny mountains can have real consequences. As the neutron star spins, the uneven mass distribution creates gravitational waves, faint ripples in space-time that carry energy away. Over time, this energy loss slows the star's rotation. Astronomers have detected hints of these mountains indirectly by measuring tiny wobbles in pulsar timing. They're a reminder that even on the universe's densest, smoothest objects, imperfection exists, and those imperfections, however small, shape the star's behavior. In a universe where even mountains are measured in millimeters, scale becomes relative, and strangeness once again becomes a norm. There's a limit to how much information a region of space can hold. According to the laws of thermodynamics and quantum mechanics, there's a maximum amount of information that can be stored in any region of space. This limit is called the Bekenstein bound, and is related to the surface area of that region, not its volume. If you try to cram more information into a space than the bound allows, the region would collapse into a black hole. This idea is deeply connected to the holographic principle, the notion that our 3D universe might be encoded on a 2D surface. It also suggests that information is physical, not abstract. Every bit of data, every particle's position, every quantum state takes up space in a fundamental way. The Bekenstein bound places a ceiling on how much complexity can exist in a given volume. It means the universe has a resolution, a graininess at the smallest scales, and it hints that reality, at its deepest level, might be more like a cosmic hard drive than we ever imagined, with limits, boundaries, and a maximum capacity written into the fabric of existence itself. Magnetars can cause starquakes. Neutron stars are solid, or at least their crusts are. They're made of nuclear matter packed so densely it forms a rigid lattice. But magnetars, with their extreme magnetic fields, experience something unusual: starquakes. As the magnetic field shifts and reconfigures, it stresses the crust. Eventually, the stress becomes too much. The crust fractures, releasing enormous amounts of energy in an instant. These starquakes send out bursts of X-rays and gamma rays that can be detected across the galaxy. In 2004, a magnetar named SGR 180620 produced a flare so powerful it affected Earth's ionosphere, even though the magnetar was 50,000 light-years away. For a fraction of a second, it was the brightest object in the sky outside our solar system. The quake that caused it was probably just a tiny crack in the star's crust, a fracture no larger than a centimeter. But the energy release was staggering. On a neutron star, even a tremor is cataclysmic. These starquakes remind us that even the most stable-seeming objects can break, and when they do, the universe listens. The universe is filled with invisible neutrinos. Right now, trillions of neutrinos are passing through your body. They're subatomic particles, nearly massless, with no electric charge. They barely interact with matter at all, which means they can pass through entire planets without slowing down. Neutrinos are produced by nuclear reactions in the Sun, in supernova, and even in the Big Bang itself. They flood the universe, outnumbering atoms by about 1 billion to 1, but we rarely detect them. It takes massive underground detectors, buried deep to block other particles, to catch even a handful. When a supernova explodes, it releases a burst of neutrinos that arrives before the light does. In 1987, detectors on Earth picked up neutrinos from a supernova in a nearby galaxy, confirming theories about stellar collapse. Neutrinos carry information about processes happening inside stars and black holes, places light can't escape from. They're messengers from the hidden universe, silent, invisible, and always moving. Even as you rest, they pass through you, untouched and unseen, carrying the history of cosmic fire. Some exoplanets are darker than coal. Most planets reflect some of the light that hits them. Earth reflects about 30%, giving it a bright blue appearance from space. But some exoplanets reflect almost nothing. These worlds, called hot Jupiters, are so close to their stars and so hot that their atmospheres absorb nearly all incoming light. One example is TRES 2b, which reflects less than 1% of the light that strikes it, making it darker than coal or black acrylic paint. Why is it so dark? The extreme heat may break apart molecules that would normally reflect light, replacing them with light-absorbing compounds like vaporized sodium and titanium oxide. The planet still glows faintly, not from reflected light, but from its own heat, like a dying ember. From a distance, it would be nearly invisible, a shadow against the stars. These dark worlds challenge our assumptions about planetary atmospheres and remind us that planets come in forms we're only beginning to understand. Some shine, some glow, and some, like Tres 2b, swallow light itself. The cosmic web connects everything in the universe. When astronomers map the universe on the larger scales, a stunning pattern emerges. Galaxies aren't scattered randomly through space. They're arranged in an intricate network of filaments and walls, with vast empty voids between them. This structure is called the cosmic web, and it's shaped by dark matter. Over billions of years, dark matter's gravity has pulled ordinary matter into dense threads that stretch across hundreds of millions of light years. Where these filaments intersect, galaxy clusters form, massive knots of thousands of galaxies bound together. Between the filaments lie the voids, enormous bubbles of nearly empty space. The cosmic web isn't static. It's still evolving, slowly, as gravity continues to pull matter along the filaments toward the densest regions. What's remarkable is how organic it looks. The structure resembles neural networks in the brain, or the branching of blood vessels. It's a reminder that similar mathematical rules can create similar patterns at vastly different scales. The universe, it seems, builds with fractals, repetition, and an elegance that spans from neurons to galaxy superclusters. Some binary stars orbit each other in hours. Most binary star systems take days, months, or even years to complete an orbit. But some orbit each other so closely, they circle in just hours. These ultra-short period binaries are locked in a gravitational dance so tight they're almost touching. In some cases, the stars are so close that their outer layers interact, transferring mass from one to the other. The more massive star may pull material from its companion, forming an accretion disk, or the two might share a common envelope, their atmospheres blending together. These systems can be incredibly hot and luminous. Some emit powerful X-rays as material spirals inward at high speed. Others pulse and flicker as the stars eclipse each other repeatedly. Eventually, some of these binaries will merge, either creating a single, more massive star or triggering a supernova. They exist on the edge of stability, held together by gravity, but constantly exchanging matter and energy. In the span of hours, they complete entire orbits. Their fates intertwined, spinning faster than most stars ever will. The universe's first light took 380,000 years to escape. The Big Bang didn't create light that we could see immediately. For the first 380,000 years, the universe was a hot, dense fog of plasma. Photons couldn't travel far before scattering off free electrons, like trying to see through thick steam. But as the universe expanded and cooled, it reached a critical moment. Electrons combined with protons to form neutral hydrogen atoms. Suddenly, photons were free to travel. This moment is called recombination, and the light released is what we now see as the cosmic microwave background. Those photons have been traveling for over 13 billion years, stretched by the expansion of space into microwaves. They carry the oldest picture we have of the universe, a snapshot from when it was just a baby. Everything before that moment is hidden, obscured by the plasma fog. We can't see the Big Bang itself, only its afterglow. But in that glow, we can read the temperature fluctuations, the density variations, and the seeds of everything that came after. The first light that escaped wasn't instant. It took time and patience, and the cooling of an entire cosmos. Dark energy might not be constant. One of the biggest mysteries in cosmology is dark energy, the force driving the universe's accelerating expansion. Most models assume it's a cosmological constant, a fixed property of empty space that doesn't change over time. But there's another possibility. What if dark energy is dynamic, strengthening or weakening as the universe evolves? Some observations hint that dark energy may not have always been the same. Its density might be increasing, which would change the universe's fate. If dark energy strengthens, the expansion could accelerate faster, leading eventually to the Big Rip. If it weakens, the expansion might slow, or even reverse into a big crunch. Current data isn't precise enough to tell us which is true, but the question matters deeply. The nature of dark energy determines whether the universe will expand forever, collapse back on itself, or tear apart. It shapes the ultimate destiny of everything. And right now, we're still trying to measure something we can't see, touch, or understand. We know it's there because of what it does, but what it is remains one of the deepest puzzles in all of science. Some planets have been ejected at relativistic speeds. Rogue planets usually drift through space at modest speeds, a few tens of kilometers per second. But in rare cases, a planet can be flung away so violently it reaches a significant fraction of the speed of light. This can happen near supermassive black holes, where gravitational forces are extreme. If a planet ventures too close, it can be caught in a slingshot effect, accelerated to incredible velocities. Some theoretical models suggest planets could be ejected at 10% or even 20% the speed of light. At those speeds, relativistic effects become noticeable. Time would slow down for the planet relative to the rest of the universe. If it collided with anything, the impact would release staggering amounts of energy. These ultra-fast rogue planets have never been directly observed, but we know the physics allows for them. Somewhere in the universe, worlds may be racing through the void at speeds we can barely imagine, silent, dark, and impossibly fast. Cast out by gravity, never to return. Quasars can outshine 1 trillion stars. At the centers of some distant galaxies, supermassive black holes are feeding voraciously. As matter spirals inward, it heats to millions of degrees. Glowing so brightly, it drowns out the light of every star in the galaxy. These objects are called quasars, and they are among the most luminous things in the universe. A single quasar can outshine an entire galaxy of 1 trillion stars. That means one black hole, surrounded by a thin disk of falling matter, emits more energy than 1 trillion nuclear furnaces combined. Quasars were most common in the early universe, when galaxies were younger and black holes had more fuel to consume. Today, they're rare. Most supermassive black holes have run out of nearby gas and sit quietly at galactic centers. But billions of years ago, the universe was full of them, blazing beacons visible across cosmic distances. When we look at a quasar, we're seeing a galaxy in its most violent energetic phase, a time when the black hole wasn't sleeping, but feeding, and in that feeding, shining brighter than anything else in the sky. Some asteroids have their own moons. Asteroids are small, irregular chunks of rock and metal left over from the formation of the solar system. Most tumble through space alone, but some have companions, smaller asteroids orbiting them like tiny moons. These are called binary asteroids, and they're more common than we once thought. the moons form in different ways. Sometimes a collision breaks off a chunk that stays in orbit. Other times, gravitational interactions during a close pass can capture a smaller object. Some binary asteroids are nearly equal in size, orbiting each other in a mutual dance. Others have one large body with a much smaller companion. Astronomers have even found triple asteroid systems where two moons orbit a central body. These tiny systems are laboratories for studying gravity and orbital mechanics on a small scale. They show us that even the smallest objects in space can have structure, companionship, and complexity. An asteroid drifting alone might still have a moon, and in that pairing, a reminder that even in isolation, the universe finds ways to create bonds. There are planets made of water. We usually think of planets as rocky or gaseous, but some exoplanets may be made almost entirely of water, not as liquid, but in exotic high-pressure forms. These ocean worlds could have water hundreds of kilometers deep, far deeper than Earth's oceans. Beneath the surface, the immense pressure would compress the water into forms that don't exist on Earth. Hot ice or supersonic water, where oxygen atoms are locked in a crystal lattice while hydrogen ions flow freely like a liquid metal. These planets likely formed farther from their stars, where water ice was abundant, and then migrated inward. They could have thick steam atmospheres or surfaces covered in boiling seas. Some might even have conditions suitable for life, though very different from life as we know it. The idea of a water world is both familiar and alien. Water is the substance of life on Earth, but on these planets, it's the dominant material, not a feature, but the world itself. Oceans without shores, stretching down into darkness and pressure beyond imagining. The Sun orbits the Milky Way at 828,000 kilometers per hour. We think of the Sun as fixed, the center of our solar system. But the Sun is also in motion, orbiting the center of the Milky Way galaxy. It takes about 225 to 250 million years to complete one orbit, a period sometimes called a galactic year. That means the Sun has only made about 20 orbits since it formed 4.6 billion years ago. And it's moving fast, roughly 828,000 kilometers per hour relative to the galactic center. We don't feel it because everything around us is moving at the same speed. The planets, the asteroids, even the spacecraft we've sent beyond the solar system, all carried along together. As we orbit, we pass through different regions of the galaxy. Sometimes we're in a spiral arm, where star formation is active. Other times we drift through quieter spaces between the arms. Our location in the galaxy affects cosmic ray exposure, supernova frequency, and maybe even the climate on Earth over geological timescales. The Sun doesn't sit still. It dances through the galaxy, and we dance with it, passengers on a star that never stops moving. Some moons have subsurface oceans. Beneath the icy crusts of several moons in our solar system, liquid water may exist. Europa, a moon of Jupiter, is covered in ice, but tidal heating from Jupiter's gravity keeps the interior warm. Scientists believe a global ocean lies beneath the surface, perhaps 100 kilometers deep. Enceladus, a moon of Saturn, has geysers that shoot water vapor and ice particles into space from cracks in its surface. These plumes suggest a subsurface ocean as well. Even Titan, Saturn's largest moon, may have a liquid water ocean beneath its thick methane-rich crust. These hidden oceans are tantalizing. On Earth, wherever there's liquid water, there's life. Could the same be true on these distant moons? We don't know, but future missions are planned to find out. Submarines and landers may one day pierce the ice and explore these alien seas. The idea that oceans exist beyond Earth, hidden beneath frozen shells, expands the possibilities for life in the solar system. Not on the surfaces we can see, but in the dark, quiet waters below. Some stars are older than the galaxies they're in. Galaxies grow over time, merging with smaller galaxies and pulling in streams of gas and stars. That means some stars inside a galaxy can predate the galaxy's current structure. These ancient stars, often found in the halo or in globular clusters, may have formed in smaller galaxies that were later absorbed. They carry the chemical signatures of an earlier era, with very low amounts of heavy elements. By studying these stars, astronomers can piece together the history of galactic mergers and the flow of matter across cosmic time. In a sense, these stars are witnesses. They've seen the galaxy change around them, watched as their original home was consumed, and continued shining through it all. They're older than the structures they inhabit, relics from when the universe was younger and galaxies were still being built. Their light is ancient, and their stories are written in the faint lines of their spectra. Quiet, old, and still burning. Neutron-star collisions create heavy elements. Gold, platinum, uranium, and other heavy elements can't be made inside stars, not even the most massive ones. The processes that create them require extreme conditions, more energy and neutron density than stellar cores can provide. But when two neutron stars collide, those conditions exist. In the final moments before they merge, the stars spiral inward, releasing gravitational waves. When they collide, the impact is catastrophic. A burst of gamma rays erupts. Material is flung into space. And in that ejected matter, heavy elements are forged through rapid neutron capture, a process called the R process. In 2017, astronomers observed one of these collisions for the first time, detecting both gravitational waves and light. Follow-up observations confirmed the presence of heavy elements in the debris. This discovery solved a long-standing mystery. We finally knew where much of the gold and platinum in the universe comes from. Not from stars, but from collisions. Violent, brief, and unimaginably energetic. Every gold ring, every piece of precious metal, was born in the merger of dead stars. The observable universe is smaller than the whole universe. When we talk about the observable universe, we mean everything we can see in principle, the region from which light has had time to reach us since the Big Bang. That's about 46 billion light years in radius, accounting for expansion. But the universe itself is likely much larger. It might even be infinite. We just can't see beyond a certain distance because light from farther away hasn't reached us yet. And because the universe is expanding, some regions are moving away from us faster than light can travel toward us. That means there are parts of the universe we will never see, no matter how long we wait. They exist, but they're beyond our cosmic horizon. This creates a strange situation. Somewhere out there, beyond the edge of what we can observe, there may be more galaxies, more stars, maybe even other observers looking back toward us. But we're separated by more than distance. We're separated by the structure of space-time itself. The universe is larger than we can ever know. Some black holes are nearly as old as the universe. In the distant universe, astronomers have discovered quasars powered by supermassive black holes, that existed less than 1 billion years after the Big Bang. These black holes contain millions or even billions of solar masses. How they grew so large so quickly is the mystery. Normal black hole growth takes time. A black hole forms from a collapsing star, then gradually accretes matter from its surroundings. But to reach supermassive size in less than 1 billion years requires rapid, continuous feeding, or an unusual starting point. Some theories suggest these black holes formed from the direct collapse of massive gas clouds in the early universe, skipping the stellar phase entirely. Others propose they grew through repeated mergers in dense star clusters. We don't know yet, but the existence of these ancient giants tells us something important. Black holes aren't just products of stellar death. They're also architects of the early universe, shaping galaxies and influencing star formation from the very beginning. Old, massive, and mysterious. Space itself might have a temperature, empty space, far from any stars or galaxies, isn't truly cold in the absolute sense. It has a temperature, about 2.7 Kelvin, just above absolute zero. This temperature comes from the cosmic microwave background, the faint radiation left over from the Big Bang. That radiation fills all of space, so in a sense, space itself has a temperature. You can't feel it because there's no air to conduct heat, but a thermometer in deep space would eventually equilibrate to about 2.7 K. As the universe continues to expand, this temperature drops. In trillions of years, it will approach absolute zero, but never quite reach it. Even the coldest, emptiest regions of the universe carry a faint thermal memory of the Big Bang. Space isn't just a void. It's a cold, glowing remnant, a field of ancient photons still traveling, still radiating, still holding the heat of creation, however faint. The universe could be one of many in a multiverse. Some theories in physics suggest that our universe isn't the only one. It might be part of a multiverse, a vast collection of universes, each with its own laws, constants, and properties. This idea arises from several sources. Inflation theory suggests that space could undergo countless localized Big Bangs, creating bubble universes. String theory allows for many different configurations of extra dimensions, each corresponding to a different universe. And quantum mechanics, interpreted in certain ways, implies that every quantum event spawns new branches of reality. If the multiverse is real, we'll likely never observe it directly. Other universes are beyond our cosmic horizon, disconnected from ours. But the idea helps explain why our universe seems finely tuned for life. If countless universes exist with different properties, we naturally find ourselves in one where the conditions allow observers to exist. It's a humbling thought. Everything we know, every galaxy, every star, every atom, might be just one bubble in an infinite foam of realities. We'd be not only small in space, but small in existence itself. Some galaxies stopped forming stars billions of years ago. Most galaxies are still forming stars, even if slowly. But some stopped billions of years ago, becoming what astronomers call dead or quenched galaxies. These galaxies used up or lost their star-forming gas. What remains are old, red stars slowly aging, with no new generations being born. How does a galaxy die? Sometimes it's because the gas was blown away by supernova or jets from the central black hole. Sometimes it's because the galaxy merged with another, disrupting the gas clouds and preventing collapse. Other times, the galaxy simply exhausted its fuel over time. These dead galaxies are often elliptical, smooth and featureless, lacking the spiral arms and blue glow of active star formation. They're quiet, ancient, filled with stars that have been shining for billions of years without reinforcement. In a way, they're fossils, snapshots of what galaxies look like in old age. And one day, if star formation continued to decline throughout the universe, all galaxies may look like this: silent, red, and slowly fading. We found planets orbiting 3 stars at once. Binary star systems are common, and we found planets orbiting both stars in some of these systems. But astronomers have also discovered planets in triple star systems, orbiting all 3 stars in a complex gravitational dance. One example is HD 188753 AB, though its existence has been debated. Another is a planet in the system GW Orionis, where 3 stars orbit each other in nested pairs. The planet orbits all 3 at a great distance. The dynamics are incredibly complex. Each star exerts gravitational force, creating shifting tidal effects and unstable regions. For a planet to remain stable in such a system, it needs to be far enough out that the stars act like a single gravitational center. From the surface of such a planet, if you could stand there, the sky would show 3 suns. Depending on the orbits, there might be times when all 3 are visible at once, casting triple shadows and filling the sky with light from multiple directions. It's a reminder that planetary systems come in configurations far stranger than our own. Some nebulae are the ghosts of dead stars. When a star like the Sun dies, it doesn't explode. It gently puffs off its outer layers, creating a glowing shell of gas called a planetary nebula. The name is misleading. They have nothing to do with planets, but early telescopes couldn't resolve them clearly. These nebulae are among the most beautiful objects in space, glowing in vibrant colors, shaped into rings, spirals, or hourglasses by magnetic fields and rotation. At the center sits the star's core, now a white dwarf slowly cooling. The nebula expands over thousands of years, eventually fading and dispersing into space. But for a brief time, cosmically speaking, it shines. The gases glow because they're energized by ultraviolet light from the white dwarf. Different elements emit different colors. Oxygen glows green or blue. Hydrogen glows red. Nitrogen glows red-orange. These nebulae are not wreckage. They're the final artwork of a star, a gentle exhalation of light and matter, drifting slowly into the dark. Quiet, colorful, and utterly transient, black holes can evaporate completely. Hawking radiation doesn't just cause black holes to shrink. If given enough time, it causes them to disappear entirely. As a black hole loses mass, it radiates faster. The process accelerates. A black hole the mass of the Sun would take an unimaginable 10⁻⁶ years to evaporate. But smaller black holes, if they exist, would go faster. A black hole the mass of a mountain would evaporate in the lifetime of the universe. At the very end, the black hole shrinks to nearly nothing, radiating furiously in its final moments. Then it's gone. No event horizon, no singularity, just a burst of radiation and empty space where the black hole used to be. This final evaporation has never been observed, and we don't know exactly what happens in those last moments. Some think the black hole leaves behind a tiny remnant. Others believe it vanishes completely, taking with it all the information that ever fell in. The question of what happens to that information is one of the biggest puzzles in theoretical physics. But one thing seems clear. Even black holes don't last forever. The Milky Way is currently cannibalizing other galaxies. Our galaxy is not a passive structure. It's actively pulling in smaller galaxies and tearing them apart. The Sagittarius dwarf elliptical galaxy is currently being stretched into long streams of stars as it orbits the Milky Way. Over time, its stars will be absorbed into our galaxy's halo. The large and small Magellanic Clouds, our two most visible satellite galaxies, are also slowly being consumed. Long streams of hydrogen gas trail behind them, evidence of tidal stripping. This process is ongoing. The Milky Way is growing, feeding on its neighbors, one star at a time. Galactic cannibalism is common throughout the universe. Large galaxies grow by consuming smaller ones. The Milky Way has done this many times in the past, and it will continue in the future. Traces of past mergers are still visible in the distribution of old stars, arranged in shells and streams that mark where ancient galaxies once orbited before being torn apart. In the silent vastness of space, galaxies don't just coexist, they devour. We may live inside a black hole. Some physicists have speculated, though not widely accepted, that our universe might be the interior of a black hole. This idea comes from the mathematical similarity between the Big Bang and the singularity inside a black hole, and between cosmic expansion and the inward collapse of matter. If true, it would mean that every black hole might contain a universe, and our universe might be nested inside a larger one. From the outside, we'd appear as a black hole in that parent universe. From the inside, we'd experience space and time expanding, much as we do. This idea is highly speculative and difficult to test, but it's not ruled out by known physics. It challenges our intuition about boundaries. If universes can exist inside black holes, then the structure of reality is far more layered and recursive than we imagined. One universe inside another, nested like Russian dolls, each expanding inward from its own Big Bang, hidden from the outside by an event horizon. It's impossible to prove, but quietly fascinating. Some stars explode more than once. Certain types of stars can undergo multiple outbursts during their lifetimes. Luminous blue variables, for example, are massive, unstable stars that periodically eject huge amounts of mass in violent eruptions. Eta Carinae, one of the most famous, experienced a massive eruption in the 1840s, brightening dramatically before fading again. It didn't destroy the star, just shed layers. Another type, recurrent novae, are binary systems where a white dwarf repeatedly pulls material from a companion star. When enough material accumulates, it ignites in a thermonuclear explosion on the white dwarf surface. The explosion doesn't destroy the star, just blows off the accumulated layer. Then the process starts again. Some recurrent novae erupt every few decades. These repeated explosions challenge the idea that stellar death is a single, final event. For some stars, dying is a process, not a moment. They flare, shed, and flare again, living in a cycle of violence and recovery, until one day, perhaps, they finally collapse or explode for the last time. The speed of light might not be constant everywhere. One of the foundations of physics is that the speed of light in a vacuum is constant, about 300,000 kilometers per second, everywhere and always. But some theoretical models suggest this might not be strictly true. In the very early universe during inflation, light might have traveled faster. In regions of extreme gravity or exotic matter, its speed might vary slightly. These ideas are speculative and not widely accepted, but they're taken seriously in some areas of cosmology and quantum gravity. If the speed of light changes, it would affect how we measure distance, time, and causality. It could alter our understanding of the Big Bang and the formation of structure. So far, every test confirms that the speed of light is constant within our ability to measure. But the question remains open at the edges of theory. If light can slow down near black holes due to gravity, could it speed up under other conditions? Could the constants of nature themselves be variable, shaped by the universe's history? We don't know. But the possibility lingers. And now, with the final anomaly softly fading into thought, let the universe grow still around you. We've drifted through mysteries and paradoxes, through signals in the dark and objects that defy explanation. We've explored black holes that spin backward, stars that vanish without warning, and planets that drift alone through endless night. We've listened to the whispers of the cosmos, the faint hums and ripples that hint at deeper truths. Some of what you've heard may stay with you, a quiet curiosity to revisit when the mind wanders. Others may fade like starlight into sleep, gentle and forgiving. And that's exactly as it should be. The universe doesn't ask to be understood all at once. It invites us to wonder, slowly, patiently, across a lifetime. You are part of this strange cosmos, made of the same atoms forged in stars, governed by the same forces that shape galaxies. And in your rest, you mirror the stillness between the noise, the quiet spaces where nothing happens and everything is. So let your breathing slow. Let your thoughts drift like dust through a sunbeam, weightless and free. The anomalies will still be there tomorrow, waiting in the dark, patient as black holes, glowing faintly like distant quasars. But for now, they can wait. For now, there is only this moment, this breath, this gentle descent into rest. Thank you for wandering the cosmos with us tonight. May your dreams be filled with distant light, and may you wake refreshed, carrying with you the quiet wonder of a universe that never stops surprising us. Sleep well.